Yeah, so I will full screen. Yes. So first I will give a brief introduction of my research group. So I'm currently a research group leader for the robotics and automation at the University of Agda. And in the group, so we have about 10 staff members, including professors, associate professors, and currently we have 10 PhD students working on the different research topics. And in this group, so we're covering different research areas, such as the main research area is focused on the robotics. So we are doing the research in the localization, planning, navigation for the mobile robots and the industry robots. And in addition, we are working on the perception innovation by using different computer vision technology and machine learning method. And for the robots, we are doing not single robot, we are doing multi-robot collaboration and human-robot interaction. And from the control automation sense point of view, we are working on the modeling, simulation, and control for different kind of systems. And for the control theory, we are currently in adaptive control, nonlinear control, robust control, and machine learning control. And for such theoretical research, we have applied the robotic technology and the control theory to the different applications, such as the marine crane operations, motion compensation, battery recycling, and industry robot collaborations. And here are also some other research topics covering the computer vision, sensor fusion, condition monitoring, and the signal process. And the application for our research, as I talked, we are not only doing the theoretical research, we're covering different applications, such as apply the robotic theory and control theory to the manufacturing, and offshore operations for the drilling operations, crane operations, and the control of the marine vessels. And in addition, we are also working on the onshore operations for different industry. And for the mobile robot, we are doing on the logistic applications, such as using the mobile robot to transport the goods in the logistic manufacturing, and also apply the robotics to the healthcare and the battery recycling. And here are the some current research projects I'm leading and involved. The first project is funded by the Research Council of Norway, and it's a large project. It's called the SFE Offshore Mechatronics. I'm currently leading the work package 3, robotics and autonomy. You can see here we have actually 6 work package in the SFE Offshore Mechatronics, from the drives, motion compensation, robotics autonomy, modeling and simulation, monitor technology, data analytics, and technology vision. And in the work package 3, robotics and autonomy, we are working on the different research areas covering the sensor fusion and perception in order to make the robot can see and can understand. And for the robot planning, we are currently the mission planning, behavior planning, and the motion planning. And to control the robot, we're covering the how we can do the control through the actuator and the sensors. And for the control part, we're covering not only model-based control and also use the learning-based control, such as reinforcement learning. And for the sensors and the modeling part, in addition, in order to have a better modeling of the systems, we are not working on the first principle modeling, but also use the learning-based modeling, such as data-based modeling technology. And in order to make the robot can understand each other's and have a good communications, we are working on the communication and network for the robots. And currently in this work package, we have 9 PhD students working on the different topics. And another project is called the Deep Cobalt project. It is also funded by the Research Council of Norway, and the period is from the 2020 to 25. And in this project, we are working on the 3 main work package. First, we are doing the decentralized control for the multi-robots, such as in these figures, we have several cases, such as you have a mobile robot working together with human operators. This is human-robot collaboration. And also we have a robot which are working on the separately and also working on the sequence. So there are 3 cases we will be considered in this project. And this project is collaborated with some industry partners, including the ABB, Omro, and the Mechatronic Innovation Labs. We also have the international partners from the USA, University of California, San Diego, KTH Sweden, and UNAV from Spain. And this project, we have 3 PhD students and 1 postdoc working on the 3 work package as given here. And 4 professors are involved in this project. And the main objective for this deep cobalt is to design and develop a new generation decentralized, not only model-based, but also data-driven deep learning-based controller for multiple collaborative robots in order that they can learn the knowledge from each other's experience and also from its own previous experience in order to perform cooperatively different complex tasks in a large-scale industry process environment. And in this group, so we also apply the robot and control technology for battery disassembling. So this is another project is funded by, we have actually 2 projects for the battery disassembling, one from the Research Council of Norway and one from EU. We're covering the dismantling and the disassembling for the components for the EV battery and also discharging and testing. So this is the robotic lab at University of Agder. And here are the educations which all the group members are teaching now. So I will not go through the details. And here are the list of the current projects funded by the Research Council of Norway. As you can see here, we have the SFE offshore mechatronics. We are working on the actually 2 work package, robotics and autonomy, and drives and deep cobalt. And in addition, we have some innovation projects, which is collaborated with McGregor, is working on the offshore cranes. And another one is the international partnership projects that is actually I'm talking here. So we have a collaboration with India universities and some other research projects. So I will not go through the details here. And the research groups, we are currently managing 3 research labs at the University of Agder. One is a motion lab. You can see here we have the 2 big stool platform, and on the stool platform we have the ABB robot, which can be used to do the motion compensation and the crane operations. And another research lab is for the deep cobalt. Here we are using the Tiago robot, you can see here, and we are also working on the UR5 robot to do the multi-robot collaboration. And the third research lab is for the battery recycling. It's called the ABB robot lab. We have 2 industry, very big robot to do the battery disassembly. And here are the collaboration in the regional, national, and the international levels. You can see here we have a very good collaboration in all over the world. So this is just a brief introduction of the research group, robotics and automation. And now I will switch to my research talk. Do you have any question? So if you have any question, you can just ask me during the talk or write on the chat box. Yes, can you see my screen here?
Yes, Rosette, please
yeah.
Go ahead.
Okay, okay. Then I will continue on this talk. Actually, today I will just focus on one of my research areas on the control part. This is my recent research work on the adaptive control of dynamics and of dynamic systems with uncertainty in the systems and quantization in the systems. Full screen. And here is the outline of my research talks. In this talk, I will covering the basic background of the adaptive control and quantizations. And then we look at the different context control structures, including different types of quantizers and different control structures. Then we look at the control design and analysis. Then finally, I will look at some examples and applications. And this talk is actually based on my current published book, the first book. I'm not sure if you can see my the point here. The first book is is published last year, and we are working on the adaptive control of dynamic systems with uncertainty and quantizations. In addition, I have also some other books focused on the adaptive backstepping control of non-smooth nonlinear case and actuator failures. So if you are interested, you can send me an email. I can send you the PDF file of my books. And then first we look at the motivation of this research. As you know that the values of the control system have been applied in many applications such as the satellites, the smart grids, different kind of vehicles and network control systems. But in these control systems, normally you will have actuator sensors to transport the signals. And in order to make the systems better and in order to reduce the communications, normally we will use some contact signals in either actuator and sensors to limit the signals when you transfer in the wireless in order to improve the speed and make the control system better. And the motivation to start the research is to consider when you use the actuator center and the sensors in control systems, we will apply the quantizations in either actuators and the sensors. So the reason is that in many systems, you are sharing the network cables in order to reduce the communication capacity. So you have to consider use such as the signals to reduce the communication capacity. And also from the security considerations in order to improve the security. So we are not able to transport all the signals in the networks. So we have to use the contact signal. And also when you look at the actuators and the sensors, most of them are digital devices. And for these digital devices, you have to use the discrete test the signals. So this is why we consider the quantization in the control systems. And then we look at the challenge from the control point of view. So from the control point of view, there are many control challenges, such as how we can compensate the sensor and actuator information when you are not able to get all the signals. You only have the limited information from the sensor and actuators. And also for such control systems, you always have the nonlinear characteristics, means that the system is not always linear. So you have nonlinear functions in your systems, how we can compensate and design a controller to deal with such nonlinear characteristics. And also for the control systems, when you do the modeling of your systems, you are not able to get the exactly model of your systems. They always have some uncertainty, you are able to model it. So how we can design a controller to compensate such modeling uncertainties. And finally, by compensate and solve all those challenges, you have to control the stability of your systems and improve the system performance. Then you will have some questions. So what can we say about the context systems? What is a context systems? And what can we do with those limited information, such as with cost quantizations? And also the third question is, how can we design a controller use only context the signals to maintain the closed loop stability and also keep the system performance still as good as your systems with continuous signal? So those are the questions and challenges I will introduce in the later. And in order to compensate and to solve the system with uncertain parameters, the most popular controller is called the adaptive control. That means that you have some uncertain parameters or uncertain functions in your systems, then you can use the adaptive control method to solve those uncertainties. And the literature review of the adaptive control is given here. So it was started in the early 1950s by using the traditional adaptive control. For the adaptive control method, they are including a different type of control methods, such as adaptive pole placement control, model reference control, model identification control, and adaptive backstepping control. So in this talk, I will apply the adaptive backstepping technology to design adaptive control for the control system with uncertainties. And since in the systems you have some uncertainty and the parameters, you need to use some techniques to estimate those uncertainties. And there are some modification techniques in order to improve the robustness of the adaptive controller, such as normalization, dead zone sigma modification, and projection. And then we look at the different type of adaptive controllers. So according to the different classifications, you can divide the adaptive control into the direct adaptive control and the indirect adaptive control, which is according to the procedure how you can obtain the control parameters. Either you directly obtain your control parameters when you design your controllers, or you can obtaining the control parameters indirectly based on the estimate system parameters. And also based on the type of parameter update loss and the corresponding stabilityness, we can also divide the adaptive control into Lyapunov based adaptive control and estimation based adaptive control. So Lyapunov based adaptive control means that you can simultaneously obtain the adaptive parameter update law and control law at the same time based on the Lyapunov stability theory. And estimation-based adaptive control is that you construct your adaptive law and control law are separate. So this is called estimation-based adaptive control. So backstepping control is actually the Lyapunov-based adaptive control, and also it is a direct adaptive control method. And then we'll move on to the quantization and the control structures. So for the different quantizers, you can based on the properties of the quantization arrow, we can divide it into two types. One is a bounded quantizer and another is called a sector bounded quantizer. And from this inequality, you can see that for the bounded quantizer, such as uniform quantizer, you will have the quantization arrow which is bounded. So we call this as a bounded quantizer. Such as uniform quantizer, you have an equal quantization level. And for the sector bounded quantizer, you can see here from this inequality, you will have the quantization arrow, which is not bounded, but depends on the input of your quantization U. So we call this as a sector bounded quantizer, such as a logarithmic quantizer. You can see that the quantization level, which is not equal, which is unequal. And but compared to the uniform quantizer, the logarithmic quantizer can minimize the average range of a communication instance, such as when you have the U, which is going to infinity, you actually have the quantization level will be increasing. So this is a two type of quantizers. And also then we can compare those two quantizers, and by combining those two quantizers into a new type of quantizer, such as called the hysteresis quantizer. And the first figure shows that if you combine two uniform quantizers into one forms, then we generate is a hysteresis uniform quantizer, such as here. And for this hysteresis uniform, you will see that in this period, you will generate the hysteresis phenomenon, which is used to avoid the chattering phenomenon, such as in the uniform quantizer. When you have the signal from U0 to U1, you actually generate a fast chattering phenomenon. So in order to avoid this chattering, you can combine these two uniform contenders together. And similarly, you can combine two logarithm contenders together and generate a similar hysteresis phenomenon to avoid the chattering. So this is why we need to consider the hysteresis compensation is used to avoid the chattering in the trajectory and in order to generate some switch dwelling time to avoid this phenomenon. And then we compare these two contenders. For the bounded contender, we know that the contendation is bounded, so it is easy to handle the effects. We can consider this arrow as such as consider as a bounded disturbance that we can compensate. But for the sector bounded contender, since the contendation arrow is not bounded, but depends on the input of contender, so it is difficult to handle the effects. So in order to compensate, you have to use some control technology to compensate these effects from the sector bounded contender. And then we look at the control structures. For the control structures, you can have the contender in either in the input part or in the sensor part. If you have the input which is transmitted through the network, and in order to reduce communication capacity, we consider we have the contender before we transmit through the network. Then we will generate a new block. And means that when you design controllers, not all the control U is transmitted to your systems. You can only use the UQ, which is your context input. So it means that when you do the stability analysis, the input to your system is only the context input. You are not able to get the pure input U. This is called the system with input quantization. And in another set, you can also have the contender in the state part. Means that when you measure your system's state X, we transmit it through the network to your controllers. And the controller can only get the contact states. So it means that you are not able to use the X in your controller design. You can also use the contact states in your controller design. So this is a system with state quantization. And sometimes you can have the both input and the state contender. Then this is a third case, system with input and state quantization. And the last structure is that in your systems, not all the state X is available, only the output signal Y is available. And the output Y will through the contender transport to your controllers. In this case, you will have system with input and output quantizations. So this is a four structures we will consider in this book. And then we compare the state quantization and input quantization. And for the input quantization, you can see that all the states X are available. Means that you can use all the state X in your controller design U. So only in the stability analysis, you can only have the context input U to do the stability analysis. So the difficulty is how we can compensate the effects from the input quantization. But for the controller design, it is still as a continuous system. You can use all the states. And then we look at the state quantization. In the state quantization, since we have the contender after the states, means that when you design your controller, you can only have your contact states XQ. So this is one challenge, how we can compensate the effects from the state quantization. And since in the adaptive backstepping control, you need to have all the states which are continuous, but when you use the context states, you will actually generate the discontinuous signal. So how we can design a controller to compensate those non-differentiable context states? This is a second challenge. So compare with the input quantization. So the design for the system-based state quantization is much more difficult than the input quantization. And then we look at the controller design. So for the controller design, I will through the input and state and input and output quantizations. Also for technology, I will use the backstepping technology. If you are not familiar with backstepping, I'm not sure. I will quickly go through what is a backstepping technique. And this is the basic structure as I showed in the before the first structure. We have only in the input container after the control U. And here we consider we have a very general uncertain nonlinear systems. Here xi are our states, and the percent I is a nonlinear function, and phi I is also nonlinear function, and theta is an unknown parameter vector. So we have uncertain parameter, which is theta. And the objective is that we have the input container, means that in your systems, you only have the context input to control your systems. And then we have the objective, how we can stabilize the systems and make the output Y can track the reference YR. And the difficulty is introduced before. So since the UQ is a context input, how we can compensate those context input. And also we have the nonlinear dynamics in your systems, psi and phi n, and uncertain parameter vector theta. Theta is a parameter vector. And then we will use the Lyapunov-based controller design by using the backstepping technique. And in order to use the backstepping technique, we need to have a system has this kind of structure. This is a kind of a triangular structure. You can see in each differential equations, xi dot, you have only xi plus 1. This is your next space. And in addition, all the psi n and phi only include the states from the x1 to xi. So this is a kind of triangular parameter state structures. Then in the backstepping technique, we will based on those how many differential equations you have. For example, in these systems, we have n differential equations, and each differential equation is first order. It means that in the controllers, you will need n step. So based on how many orders your system has. And for each controller design, you just look at the one single differential equation corresponding to each one. For example, in the step 1, we're just looking at the day1 dot. What is the day1 dot? Is just related to your x1 and the reference. Means that we just look at the first differential equation x1 dot and use the Lyapunov-based technique, try to design a virtual control, which is called alpha1, which can stabilize your first order differential equation. Then corresponding to the step, at the I steps, you will have your virtual control alpha I, which can make sure all the previous I steps are stabilized. Then in the last step N, you will have your context signal QU, and in this step, you will generate your final control U, and also generate the adaptation parameter law, which is used to estimate those unknown parameters theta hat. And the advantages of the backstepping technique is given here. It is a recursive step, as I talked. You corresponding to each differential equations, then design a virtual control alpha I corresponding to each differential equation. So this is a recursive design. And also it is a Lyapunov-based design. You have to choose your Lyapunov function and make the V dot is less than 0. And it's a flexible technique and guarantees the stabilization and tracking properties. And then since the QU is only in the last step, so the challenge is only on the last step. All the previous n -1 step is actually same as normal backstepping step technology design. Only in the last step, we have the context input. So we have to do some modification in your controller to compensate these effects. And then we look at, in order to compensate those context inputs, we will use the tangent hyperbolic functions in the U, that is your final input. And here you have the Dn and Un. Un is called a virtual controller, is designed by here. And in the Un, you will find that we will also have another tangent hyperbolic functions, which can include in your last states, the Dn and mu is your context parameters. And in the parameter estimation loss, we introduce a sigma modification by compensating the uncertainties and the context states. And the stability analysis is based on the Lyapunov technique. We will construct a normal Lyapunov function, which including all the states, Li, and the parameter estimation theta tilde. And by using those kind of designs, we are able to compensate. That we will look at. So in order to compensate those contact states in this lecture, we consider the Q contactor is a sector bounded contactor, means that the contactation arrow is not bounded, but it is sector bounded. It's more general contactors. And by using the tangent hyperbolic functions and by using the contact the sector bounded properties, we can transfer the DNQU. The challenge is that the U is inside your contact the signal. So how we can bring out U from the contactor, then we can design it directly. So by using the property of the second bounded contactor, we can transport the DNQU to a function of the DNU. Then we can separate U outside from the contact scale. And then we use our designed controllers by using the properties of the tangent hyperbolic function and our new controller design. We can transfer this part by directly with the virtual control UN. Then you can, based on the normal standard backstepping technology, to design the UN in order to compensate all the nonlinear dynamics in your systems. So this is a key technology used in this controller design. And then the Lyapunov stability list. I will not go through the details, but by using this technology, you can get the last equation and inequality as given here. You have UN dot is less than minus F1 is a positive constant times UN and M1. And this will show that all the signals in your UN are bounded. And then you will be able to generate the following theory, such as we can guarantee all the states in your closed loop systems are bounded. And also we can generate the tracking arrow, which is bounded by a constant B1, where B1 is based on your initial Lyapunov function and also based on the M1 and F1. And M1 you can see here, which is based on the quantization parameters and your initial state theta 0, and F1 is based on your control parameters. Ci to Cn is your control design. It means that you can tune your control parameters and tune the quantization parameters to reduce this tracking arrow B1. So it means that the tracking arrow can be tuned by design control parameters and the quantization parameters. And we also extend our result to the dynamic contactor, means that your quantization parameters are not exactly known. You can design the quantization parameters in parallel with your controller design. And in order to design this dynamic contactors, we will use some parameter estimation laws, mu hat and rho hat, to estimate the quantization parameters. So where the U hat and the rho hat are estimates of the quantization parameters. And the controller design is actually same as the previous fixed contactor. And then we move to the state quantizations. And for the state quantizations, as I said before, the challenge is that in your controller design, so you can only use the contact the states FQ. And in these systems, we also consider we have the nonlinear dynamics and uncertain parameter theta. And then we look at what are the challenge. So when we use the backstepping controller design, we need to have all the system states are continuous in order to generate the differential derivatives in the following step. But when you have the contact states, such as here, in the first step, you have, since we only have the contact states where X1Q represent your contact states. As we know that in the contact state, this is not smooth continuous. It is actually discontinuous. So when you do the derivative of your alpha1 dot, since this x1q is not a smooth continuous, so means that this is not it is not differentiable. So how we can use such context states in the backstepping design in order to design the controllers? This is a challenge. How we can solve those non-differentiable virtual control function to guarantee the stability of your systems. So the key design technique is given in the following design procedures. So first, we just assume we have the system with continuous states. Then we follow in the basic backstepping technique to design our virtual control and final control U. And then we keep these partial derivatives not changed. So this is all step 1. Step 2 means that we consider we have continuous systems without context signal, then design controllers and calculate the partial derivatives. And then we move on to the context states. Then we will design the new controls variables alpha, I bar, and ut, whereby just replace the old continuous states by the context states. Means that you just use xq to replace the x in your previous steps. Then we choose the suitable design parameters so we can guarantee all the system are bounded and we can maintain the system stability. And then we look at this is our final control. The control structure is actually similar like the normal backstepping technology, and we just replace xi by its context states. Means that we replace x1 by x1q, means that this is your context state. And we keep these blue terms. This is a partial derivative as continuous. So this part is not changes. And if you calculate this partial derivative, you actually get this is a constant. And in the parameter estimators, in order to guarantee all the parameters are bounded, so we use a projection in order to guarantee all the parameter estimates are bounded. And the virtual control laws are same as just replace the states by its context states. And then in order to tackle the challenge, so you have to use some preliminary results based on the relationship between the context states and the function without context states. So the first lemma one will generate the relationship between the function with the context states and without context states. We generate the following inequalities, and the lemma 2 is we relate our states with our virtual control Z, so we get those relationships. And then based on this lemma 1 and lemma 2, we choose the Lyapunov function as the same as previous with input computation. Then we can replace the context states, get the relationship between the virtual control alpha q with your original alpha n, and we have the relationship between the percent x bar, which is your continuous states, and the x bar q is the context states and similar. Then based on the lemma 1 and the lemma 2, we can guarantee the last inequality, which is shown in the last line. Then we can guarantee V dot is less than the old states Zi, which is minus, plus M is positive constant. Then we can show that all the states Z is bounded. Since the theta hat we use projection, then we can guarantee all the Zi and the parameters theta are bounded. Then we get the following theorem, which is show that by using such kind of controller design, we can guarantee all the closed loop signals are bounded, and also we can guarantee the stabilization arrow, that is also the tracking arrow, is actually bounded by a constant M and theta. And M is depends on your design parameters, system functions, and quantization parameters. And the sigma is actually a parameter. You have to choose your control parameter, C, which is the minimum of all your control design parameters, satisfy these inequalities. This is a condition we have to satisfy in order to guarantee the stability. So this is for the system with state quantization. Then we look at the last two cases, which is by combining the input and state and input and output. For the input and the state quantization, I will not go through the detail. It's actually combine all the technology for the system with input and system with state. Then we combine them together, we can design a controller to compensate both input and state quantization. And for the input and output quantization, since in this case, we have only the output signal Y is available. But in our systems, we have the states Xi to Xn, but X2 to Xn are not available. So in order to design controller, you have to use the observer to estimate all the states which are not available. So we will combine the observer design and the input and the state quantization technique to design the controller. And the design the observer-based adaptive controller is based here. First, you have to design an observer to estimate all the states X. And then you will generate this X hat, which is estimate of your measured states. Then you will use X height and in your controller design to generate context input and the state quantization to compensate both input quantization errors and state quantization errors, and also combine the observer design. And since in the observer design, you have YQ, which is your context output. Since the YQ is not the smooth continuous, so in the observer design, we will use the non-smooth analysis technique. It's called the Philippov solutions to do the stability analysis. And then we can see that the both controller and the observer is actually including the parameter L, where L is actually a parameter which is estimated by using these differential equations. So this is a controller including the observer and the parameter estimation loss, which are combined together. So it means that the observer and the controller are designed simultaneously, not separately, which are connected together. And finally, in the stability analysis, we have to consider the several Lyapunov functions in order to guarantee that all the system states parameter estimator, state estimator are bounded. First, we include the Lyapunov function V, which is include the estimation state estimation error and the system states in order to prove the L, which is parameter, is bounded. And then we consider the second Lyapunov function, which is used to prove the state estimate Xi hat is bounded. Then we have the last Lyapunov function, which is used to prove that all the rest of states are bounded. So 3 Lyapunov functions are considered in the stability analysis. And finally, we can show that the system estimate output Y is bounded by these parameters. And then we look at the some extensions. Since in all the previous system, we consider we have the single input and single output systems. And actually those technologies can be applied to your have the multi-systems which are connected together, such as here you have 4 subsystems which have connected through some information exchange, where the information can be contested state or continuous states. So this is one application for the interconnected systems with interactions. And then we also apply our theoretical research to some real applications. One application is by apply the adaptive controllers to control a rigid body system with input and output quantization, where the rigid body system can represent a lot of different types of systems, such as helicopters, drones. And in this paper has been published at Attribute Transition Industry Electronics, which is with theoretical result and experimental result. And in the experiment, we use the concert aerial, which is like helicopters, to verify the theoretical results. And another application is that we apply the adaptive control technology to crane operations, which we do the theoretical results with a simple crane and to compensate the parameter uncertainties and the motion compensations. So this is another applications. And this is what we verify our result for the helicopter. We use the concert aerial, I'm not sure we have the video. So this is the theoretical result. And then I will just give a conclusion and some challenge for the future topics. First, in this talk, I address how we can design the adaptive control to the system with uncertainties, nonlinear dynamics, and quantizations in the different structures, including the input quantization, state quantization, and both input and state quantization. And we show that how the effects of the quantization in control systems can be treated and dealt with in a unified and systematic manner by using adaptive backstepping technique and the Lyapunov technique. And we also apply all this theoretical research to two applications. One is helicopter control and another is crane control. And for some research directions, since in this works, we only consider the adaptive, means that how the uncertain dynamics can be dealt with, the fast and the robust is not the main focus. So how we can improve system performance by generating the fast and the robust and adaptive properties to those uncertain dynamics is one direction. And also in this talk, we only consider we have the signals which has context by different type of context. But for the limited information, so you may have different discontinuous properties. You can apply such technology to deal with, such as you have different networks which are communicated with only limited information. So means that, for example, you have a signal triggering at such times, then you can use those control technology to deal with such problems. And also we can apply those control technology to multi-agent systems, which is actually an example for the large scale systems. And when you have systems in the networks, especially cyber-physical systems, you need to consider the security reasons in face of attacks and constraints. This is another applications. And also some other different applications such as robotics industry manipulations, drone, different helicopter controls, which can also consider one directions. Here are some reference, and here some of my collaborators related to this research. And I'm also thanks to the sponsors from Research Council of Norway and UER Priority Research Center. Yes, thank you very much.
Thank you, Professor Jing. Any questions? Any analysis on the sensitivity of the quantization? Hello.
Hello. Yes.
Hi, Professor. Is there a just would like to know if the sensitivity analysis, how does it affect the quantization? How does the quantization affect the sensitivity?
You mean how the quantization affects the system performance?
Yes, yes.
Yeah.
Because of the yes. Because of
yeah,
the quantization, are there any reductions on the?
Yes, it's definitely will affect the system performance, but through our from the theoretical result, you can see that if you have a small quantization error, you definitely have a better performance. If you have a large quantization levels, your performance will be bad. But from the experimental result, we actually try the different quantization levels, but the results show that there are not too big difference between the for the different quantization levels. And also for the state quantization, if you look at the theoretical result, we have the one inequality, means that the quantization parameters must to satisfy this inequality in order to guarantee the stability analysis. So it means that the quantization level cannot be too large. Otherwise, your system will become too unstable.
Thank you, Professor Jing. Thank you very much for participating and delivering a talk in the workshop.
Yeah.
So we during the workshop we had an overview of the learning methods in the first 2 days, and we had a couple of talks, including yours, on the systems today.
Yeah, it's actually quite interesting. As I mentioned in my another project, it's called Deep Cobalt. We are working on the deep learning and the Q-learning and the reinforcement learning. So if there are some students and staffs and scholars are interested in visiting us, we are very happy to host them. Since this project is an international collaboration project, so we need to have some collaboration between UER and your university.
Sure.
So, yeah.
We would be glad to pursue on that. Thank you very much.
Yeah, thank you. Yeah. Bye.
Bye then. Thank you.
Bye.